Hello, everyone. My name is Guy Eichler, and I'm going to present to you our work on MasterMind, a Many-Accelerator SoC architecture for real-time brain-computer interfaces. Brain-computer interfaces enable the bidirectional interaction between brains and computers. In recent years, there is a growing interest in BCI among academia projects and industry companies. A few examples are Neuralink, BlackRock, and Control Labs. Our goal is to create BCI systems and devices that can work as close as possible to the human body, or in other words, in a body area network. That means we need to comply with two main conditions. One, the system needs to complete operations in real time in order to react to the information coming from the brain, which means in less than 0.18 seconds, the brain's average reaction time. Two, the system needs to meet ultra-low power constraints of 200 milliwatts in order to be located as close as possible to the human body as an edge device and the BCI wearable. In our work, we focused on hardware acceleration of the algorithms that analyze the brain data. We used an open source SoC design platform called ESP as the base structure of our SoC architecture. MasterMind is a configurable accelerator-based SoC architecture that is designated for a promising BCI algorithm called HIWA. We contributed our broad design space exploration, including efficient implementations of the accelerators and the SoC. We also released MasterMind to the public domain. The algorithm we chose to focus on is a machine learning algorithm called hierarchical Wasserstein alignment, or HIWA. The algorithm succeeded in matching neural activity from the brain of non-human primates to body movements. As you can see on the right, the core computation of the algorithm is a while loop, running two kernels, one after the other, until a norm check is satisfied. One of the kernels is the synchron algorithm, and the second is singular value decomposition, or SVD. In the bottom figure, we profile the state-of-the-art Python implementation of HIWA. You can see that synchron is the main bottleneck, responsible of 88% of the execution time. Because of that, synchron would be a good candidate for hardware acceleration. In order to further accelerate HIWA, we decided to implement SVD in hardware as well, and by that, have the ability to isolate the main bulk of computation from software and offload it into hardware. Our target system is composed out of three main parts: an implantable chip, a separate system on chip, and a database. In this work, our main focus was on the SoC that is designated to execute the BCI algorithm. The SoC should provide results in real time and maintain low power consumption. The flow of the system starts with an offline phase of gathering data and storing it in a database. In our case, the data are body movements. Then, in an online phase, the neural interface on the implanted chip is used to record brain data, followed by the process of spike sorting to distinguish electrical spikes. After that, the data is transmitted through wireless communication to the MasterMind SoC. Our tile-based SoC executes the HIWA algorithm using designated hardware accelerators, RISC-V processor, memory controller, and I/O. As provided by ESP, our SoC includes a network on chip as the main on-chip interconnect and supports point-to-point communication. The point-to-point feature allows direct data transfer between accelerators without interaction through main memory. Our SoC also comes with the full software stack for offloading the HIWA computation to the accelerators from a Linux user space application. For the computation itself, the data from a database is retrieved and HIWA matches it to the brain data in order to output the best matching body movement. Then, this output can be forwarded to an external device for correcting disabilities. For our SoC, we designed two accelerators, one for synchron and the second for SVD. We decided to separate our design into two accelerators. We did that because of the computation complexity of both kernels, the different execution times, and also to allow reusability of each kernel in other algorithms. Both accelerators have three main models: load, to load the data through DMA, compute, to execute most of the computation, and store, to send out the final output. The SVD accelerator was implemented in Vivado HLS and synchron in Stratus HLS. Both accelerators compute with a 32-bit fixed-point data type. They take advantage of various HLS knobs, leverage pipelining, loop unrolling, Taylor series approximations, and double buffers in order to overlap communication and computation. As shown in the figure in the bottom right on the SoC, the data transfer between accelerators goes directly through point-to-point communication, while the only interaction with main memory is in the first and last iterations of HIWA. We conducted design space exploration at the accelerator level and at the SoC level. At the accelerator level, we increased the usability of our accelerators by creating various implementations that emphasize different design trade-offs. At the SoC level, we uncovered information that can be used in order to choose specific SoC configurations for constrained BCI systems. We evaluated our Many-Accelerator SoC on FPGA against 3 platforms: Intel i7, ARM Cortex-A53, and RISC-V CVA6. We used the CVA6 processor as the baseline. On the top left, you can see an evaluation of the execution time of our accelerators in isolation compared to our own optimized C++ software implementations running on the general purpose processors. Both accelerators achieve significant gains with respect to CVA6. The software running on i7 and ARM is still faster due to a much higher clock frequency of 1.2 to 3.7 gigahertz, while the one on FPGA is only 78 megahertz. On the top right, you can see an evaluation of performance and energy efficiency. It compares between our multi-threaded software applications running on the general purpose processors and various SoC configurations with different numbers of accelerators instances. An SoC with point-to-point communication enabled and only one accelerator from each type provided similar performance to ARM with 8x better energy efficiency. An SoC with 4 instances for each accelerator gave similar performance to i7 with 71x better energy efficiency. In addition, enabling point-to-point communication for Hiwa can provide over 90% off-chip memory access savings, which means it can greatly minimize off-chip energy consumption. As our final goal is to build ASIC chips, we use Synopsys Design Compiler to estimate the performance and energy gains of MasterMind implemented with ASIC technology. The projection showed additional 13x speedup and 79x better energy efficiency over the FPGA prototype. That SoC will meet the thresholds that enable real-time and energy-efficient BCI, with execution time of 0.15 seconds and power consumption of less than 200 milliwatts. We designed MasterMind with the goal of advancing the system-level design research in SoC architectures for brain-computer interfaces, a field of computer engineering that is growing remarkably in importance. MasterMind is inherently flexible, as it can seamlessly accommodate the integration of many other accelerators. MasterMind is also scalable, as it supports efficient point-to-point communication schemes among accelerators that improve performance and energy efficiency by reducing memory accesses. We released the contributions of this work to the public domain in the following link. We hope you enjoyed our presentation and that our work will encourage further development in the field of BCI system design. Thank you for listening.